Hey Royals, in today's lesson we're going to look at some scientific math. So it's not math necessarily to our physics course, but more important, math that you would use in any of our science courses at John F. Ross. Okay, so one of the things we're going to talk about is accuracy versus precision in a lab setting. We're also going to look at determining how close a measured value would be to an accepted value or another lab group's values. Okay? And then we're going to go into the part of the lesson that you're going to read on your own, but it will deal with some significant digits or certain digits. And then we'll come back and we'll do a few examples together for certain digits. Okay, so diving in, what the heck do we mean by precision? So imagine you're in a lab setting and you're given a ruler. Now you look at the ruler and it goes down to centimeter increments. And you think, I can do better than this. So you ask Mr. Braithwaite for another ruler and he gives you one that has millimeters on it. Now you've taken a tech class and you know that there's something better than that, and they're called calipers. And calipers can actually measure down to very accurate measurements down to the orders of like fractions of a millimeter. Now, that would be something that is very, very precise. And what we mean by that is repeatability. So with, say, something like calipers, you can actually be very good with repeating your values. So what I mean by precision is a repeatability. Let's fix that. Repeatability in your measurement. So if I came up and I measured it again the next day, I would get the same value. And if I measured it again the next day, I would get the same value. So it would be the same precision. With the same tool, I'm going to get the same measurement. Okay, so now imagine that I take a ruler and the ruler has an increment. I'm just looking around my desk for one. Has the centimeters starting right at the edge. Now I have another ruler that centimeters start maybe half a centimeter in on the ruler. Now if I'm always measuring with the same tool, with one of these I might be more accurate than the other, right? It just depends on how I use the tool. If I'm lining up the edge of my ruler with the edge of the object I'm measuring, say right here, then I would probably get the same accuracy every single time. But if I'm going to use my ruler and the zero starts right here, that means that I'm always going to be off by the same amount, right? So that's what we mean by accuracy, how close it is to a measured value. And so I have an example here where I take the mass of two objects and I'm trying to determine which one is more accurate and which one has more precision. Now, mass of object A was at 155.22 grams, and mass of object B was 142 grams. And what if I told you that the actual accepted value was 145? Well, you would know that this first one is actually 10.52 grams too large, right? I've measured it to be overly massful. Now, this other object, 142, would actually be 3 grams too small. Now, accuracy-wise, I want you to think about this. Accuracy-wise, which of these two measurements would be better? Now, would you have the same result if I asked you for precision? Which of the two measurements was more precise? And I'm hoping you're telling me that the two answers are not the same, right? If I'm looking at the case here, this 155.52 grams, it is more precise because I am more certain down to a higher degree of decimal places, right? I can be more precise with my measurement because my tool was able to get me 2 decimal places, where the same thing is not true about measurement B. It only had 142. There was no decimal places that I could be certain about. Okay, so when I'm looking at this sentence, it says if the accepted value is 145 grams, then measurement blank would be more precise but less accurate. Well, more precise, we said, was measurement A. It had more decimal places. I was more certain on that measurement because I was able to report 2 decimal places. Whereas measurement B is more accurate. It's closer to that accepted value, but it's less precise. It means that I wasn't as certain about the measurement that I came up with. Okay, so let's talk about what we mean by precision and accuracy a bit more. Right, so I have some bullseyes here for us to look at. These bullseyes give us a sense of what we mean by precision and accuracy. So if I look at the very first bullseye, I would say that all of my measurements are very close to the accepted value, or the middle of our bullseye. If we accept that the middle is what we're trying to get to, then all of my measurements are really, really close to it, which would mean that my accuracy is very high. Now, my precision is repeatability. So if I look at the dots that are on my bullseye, they're all very close together, which means that my measurements were all very close together, which means that I have a high level of precision. Okay, so if we continue with this idea, again, these are all clumped together, which means that my measurement was always repeated. So that would mean that I would have a high level of precision. But my accuracy is not as good because I'm off from what I'm actually supposed to be measuring. So I'm going to say that that has a low level of accuracy. Now, same idea here. The average, if I average all of these out, I probably get something close to the middle, which means that my accuracy is actually quite high because the average value, if I took the average of my measurements, I would probably get pretty close to the middle of that bullseye. But my precision, my data is all over the place. I have some that are up over in the top right. I have some that are in the top left. I have bottom left, bottom right. My measurements are all over the place. So I say that whatever tool I used had a low measurement of precision. Okay, so then if I look at the last one here, if I'm looking at this bullseye here, if I took the average, I would probably get somewhere in here. Now that is pretty bad for accuracy. So I would say that my accuracy is low and my precision is low, partly because my data points are, again, spread out. Okay, so that's, I hope you understand the difference between precision and accuracy. And so we want our data in labs to be as precise and as accurate as we possibly can. So that means using the right tools. If you're going to measure the length of a pencil, don't go grab a meter stick. If you're going to try to, in chemistry, measure the pH of a acidic solution, don't grab phenolphthalein. So use the tools that will give you the correct responses, or as accurate as you possibly can be. Okay, so we're going to actually talk about experimental error and percent differences. And there's certain reasons why we use these things. So if I was going to measure the speed of sound, I know that room temperature speed of sound is 340 meters per second. But if I go outside and I measure, say, 320 meters a second, I have a level of uncertainty or error in that measurement. Okay, so if I ever have a, say, one measurement, measured value, and one known value, I'm going to calculate the experimental error. I'm going to find out how far off is my data from something that is a universal constant, something that we know the answer to. And for that, we're going to take the difference between my measured value and the accepted value, and I'm going to do the absolute values. So the absolute value bars here mean that I'm only going to take the difference of the two. So for example, if I was trying to measure the difference between 10 and 9, if I do the subtraction this way, I get 1. However, if I did 9 subtract 10, I get -1, right? But if I take the absolute value of the difference, in both cases, I get +1, right? So I'm only looking at how different are they. So essentially, absolute value bars are taking the positive difference. No matter what order I do the subtraction, I'm only looking for the positive of the difference. Okay, so for experimental error, I'm going to then divide by the accepted value. So I have an example here that deals with our two measured values from before. So measurement of mass A and measurement of mass B. Okay, so if I want to find out which of these two measurements actually has a smaller experimental error, I can actually go ahead with that. So I measured 155.52 for mass A, and I'm going to subtract it with the known 145. I find the difference between those, divide by 145, and multiply by 100%, tells me that mass A actually had a difference of 7%. Now, that means my value was off by 7%. That's not too bad. I would say anything below 10% is acceptable. If I did it with measurement B, of which we measured 142 grams, we would get a experimental error of 2.1%, which is a heck of a lot better than 7%. Okay, so if I was in a situation where I had two measured values, so say I'm in doing a lab, I'm trying to find the acceleration of a car from a stoplight, and I measure it and my friend measures it. And we want to find out how different our two values are. We don't want to just look at them and go, they're pretty close. We want to be able to determine exactly the percent difference between these two measured values. So that means with percent difference, we have two measured values. Okay, so you can see the difference between when I'm going to use experimental error and when I'm going to use percent difference. Okay, so with percent difference, the numerator is the exact same. I'm going to take the absolute value between two measured values. But in the denominator, that's this whole thing here, that is the average of measurements. Oops. It keeps jumping on me. So we're going to zoom in here. So that's the average of my measurements. Okay, so let's say, for example, I'm trying to measure the speed of sound, and one lab group gets 345 meters per second. The other lab group gets 342 meters a second. And I want to determine how different are these two values. Well, just like we did before, we're going to take the difference between the two measured values and find the absolute value between them. And then I'm going to divide it by the average of my measured values. So because I have two values, I'm going to divide by 2. Okay, so I get 345 meters per second plus 342 meters per second divided by 2. And then I'm going to go through with the difference in the numerator divided by my denominator, multiply by 100%, and I get 0.87%, which tells me that the two measured values for the speed of sound were extremely close. Okay, so now the next thing we want to talk about is certain digits, or what I call significant digits. Significant digits, or sig figs, or significant figures, something like that. It's telling you how precise my measurements can be. So I'm going to pause. I'm going to let you read through this note here. And then once you've read through it, come on back and we're going to do a couple examples together to determine the number of significant figures in a series of different operations. So addition, subtraction, multiplication, division, and then a combination of things. All right, so now let's take a look at some operations with these certain digits. Now, there's certain rules that we're going to do when we're adding and subtracting values, or we're multiplying and dividing values. Okay, so let's start in on discussion of what do I do if I'm adding and subtracting values that have different levels of precision. So with these adding and subtraction, I'm going to have the result have the same precision as the least precise number. So remember precision, the more decimals that I can be certain about, I'm more precise. So I'm looking at the number that is the least precise. So essentially the weakest link in my calculation. So with addition and subtraction, it comes down to the definition of how many decimals do I have. Okay, so what I'm going to do is I'm going to add all of these together and I'm going to determine how many decimal places I have. So I'm going to add this together. So 2.41 plus 3.57 plus 2 plus 4.9 comes out to 14.882. Okay, so if I look at this, I want to find out how many decimals can I report and not be making up data, right? Because the worst thing I could possibly do is give a number that is more precise, because it's kind of lying. It's saying that I'm able to measure to this level of accuracy or precision, but really you can't. Okay, so the first one, this 2.41, has 2 decimal places. I'm going to use DP for decimal places. The second one has 2 decimal places as well. This 4.002 has 3 decimal places, and the last one here has 1 decimal place. So I want to measure to the number that is the least precise. So the least precise in our case here is 1 decimal place. So I want to report my answer to 1 decimal place. So that means 14.9, because this 8 would actually be the 1 decimal place, but I look next door to make sure that I'm not rounding up or down. In this case, I'm rounding up. So my answer would be 14.9. Okay, so here I'm saying complete the full calculation and then worry about your significant figures. Okay, so that's what we're going to do. We're going to do the whole calculation and then worry about how many significant figures I should hold. Okay, now with multiplication and division, there's a slightly different rule that we're going to want to use here. So I want to use the answer, or the calculation that has the least number of significant figures or certain figures. Okay, again, the weakest link is going to define this. So go through the calculation and then determine which one is going to be your weakest link. Okay, so I'm going to go ahead here and I'm going to say 2.4 multiplied by 17.2 comes out to 41.28. I'm still going to multiply by 11.55. Now, if this was the end of my calculation, I only had these first 2 terms, the 2.4 and the 17.2, I would have my answer come out to 2 significant figures, 41. And that's from the fact that this value here only has 2 significant figures, whereas the 17.2 had 3 significant figures. And I'm not going to use that one because I want to use the one with the least number. Okay, so I'm going to continue with my calculation. I'm going to multiply all of this together as if this was the beginning of my question, and I'm going to say that my answer is 476.784. Now remember, I can only report my answer to 2 significant figures. So my answer has to come out to 4.8 times 10 to the 2. And that's because I can't report 476 into significant figures. So I'm going to report it as 4.8 in the fact that I have to round upwards times 10 to the 2 to give me that level of accuracy and precision. Okay? So here it comes down to sig figs. Okay? In the last case here, when I have a combination, what happens if I have multiplication and I have addition? Which rule wins? It comes down to our friend BEDMAS, or order of operations. Okay, so let's go ahead with it. So BEDMAS would mean that I want to do my division multiplication first. So 29 times 2, I get 58. And then I have to add 18.0. And I'm going to carry all of my values here. And I'm going to then say, all right, if I were going to round right now, this would only have 1 sig fig. I would have to round it to 60, or 6 times 10 to the 1. Right? But I'm not going to round midway through my answer. I'm going to carry every digit until my last answer, which means that my addition here becomes 76.0. And because I can only report 1 sig fig, this becomes 8 times 10 to the 1. Okay, so if you have any questions with any of this stuff, please reach out to myself and I'll be happy to help you out.